and welcome to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Scott Cain.
Thank you, William. And thank you, everybody, for joining us for another KYZEN Tech to Tech. So today, we're going to be talking about overcoming cleaning challenges for AI devices. And as you obviously know, AI is artificial intelligence. It's been on every advertisement we've seen for the last 3 years. But today we're going to talk about what goes on with those devices in the manufacturing process and the cleanliness challenges that come along with that. Right? We've seen more of these in our environment, and there's a lot of challenges that come with the cleanliness required for the product reliability that the customers demand for this. Some of those include intricate geometries, low gap heights, maybe some larger die sizes, what materials are being used, how do they engage with each other, how do we make sure that those materials are not affected by the chemistry and water in the application. One of the most popular package types that you will hear about is CoWoS, and that's the chip-on-wafer-on-substrate. And really what the recipe for that is, it's the integration of the silicone on chip and the HBM, which is the high bandwidth memory. It's bonded to a silicone interposer with TSVs, which are the through silicon vias, which is bonded to a PCB substrate. And kind of what that looks like you can see on the right-hand side. So, but as these new packages are introduced, how we cleaned in the past really is not effective. You know, the traditional protocol standards and recipes for like flip chip, they're just not robust enough for the CoWoS applications. So as an industry, we need to reevaluate how we clean and then the relationship between the variables for reliable cleaning. So real quick, why are we cleaning, right? Well, we want to increase the reliability. So what happens is if the residues are present on the parts, you're risking electrochemical migration, corrosion, and CAF. And if that happens, what's going to happen with the part? Well, it affects the thermal management. It lowers the output or the yield during production and a short life that can lead to the premature failure. And that actually leads to performance failures and the financial fallout, right? Your customers expect a certain level of quality. If the parts are failing, you're not hitting that quality level. You're spending more money to try to upgrade your production to offset yield failures. There's a lot of things that go on if we don't clean. And so that's kind of why we're cleaning and making sure that we're optimizing not only the production floor, but what's happening with the reputation of your company in the real world environment. So what was the goal of this experiment? Why did we spend time on this? Well, as the complexity increases, we need to evaluate process optimization and see what we can do to optimize that. We wanted to evaluate and determine the relationship between the variables involved in cleaning and how can we extract the right information from that to optimize and validate our cleaning process. So by separating the variables and evaluating the results, now we have some guidance for optimization. Everything's got to be optimized itself, but this provides a roadmap to get us to the right portion. So how did we test this? What was the methodology for this? So KYZEN built this machine. It's got a 5 horsepower motor on it. It's got a placement for a single die with a spray nozzle. Obviously, it gives us the ability to videotape everything that's going on and take pictures. And we have 50 by 50 dies where flux is put in between the 2 dies, and we added a little bit of food coloring to it, so we're actually able to see it. So how does that look? We'll take a couple seconds here and we can show you kind of what it looks like with the nozzle going across, and you can see the flux being removed from under the die. So how do we process this information, right? The information is only as good as what we can extract from it. Our team created a Python script that saved a copy of these images with the area of flux marked. And then, of course, we did a back check on that to verify that the accuracy and the data that was extracted from the Python script was in alignment with what we were seeing in the real world. And then what it did is it generated values that were exported to an Excel file. but the data was normalized and set the initial image to 0% clean. And that's really important, right? Because we're putting the same amount of flux on there, but some of it's going to, those slides might not look the same, but what we're doing is saying when we're starting, it's at 0% clean. So if we look at these images that are below, the initial image is on the left and what we processed was on the right, but that was at 0% clean, even though there's some of that where we might go, it could be perceived as clean. For this experiment, once it started, it was at 0% clean. So here are our testing parameters, right? We have two different fluxes involved. We have a chemistry that we know is optimized for one of these fluxes. The other one we don't think is the right solution for this flux. We ran everything at 3% concentration, so that was not a variable in this experiment, but we had different times, pressures, and temperatures. So you can see the time, we ran it at 1 minute, 5 minutes, 30 minutes. The pressure was at 5.5 bar, 7 bar, 8.3 bar. And then the temperature was at 50, 60, 70, 80 degrees C. We did that for flux 1 and flux 2. So there's a number of experiments involved in this. But what we can do is we can take that information, extract what the variability was between each variable, what the effect of it was, and then start to dive into that information. So if we look at the WS1, which is the flux we feel like we had a better chance with. We've had experience with it and knew that the chemistry in this flux worked really well together. One of the main things that we want to point out, anytime you're looking at any sort of graph, you want to see what the range is and make sure that that's consistent between all your data points. So for this one, we can see that 0.0 is completely clean. And at the top end, we start from 0.8. So let's look at what happened with time. That all makes sense, right? The longer that it's in the process, the better the cleanliness is going to be. So we can see what happened from 60 seconds to 5 minutes to 30 minutes. That all totally makes sense. What may be new information that we have extracted from this was that the pressure, as we increase the pressure, the cleanliness results actually don't get any better. In a sense, they get worse, right? So at 5.5 bar, we're really clean. When we increase it up to the 7 bar, not as good. And as we go to 8.3 bar, even worse than the 7 bar. And then what happens with temperature, right? This is interesting as well. The temperature, 50 degrees, works really well. We go to 60, not as well. 70, not as well compared to the 60. But then when we go to 80, it gets really good. So this is really good information, right? Because at 70 degrees, you're not getting as good as if you just increase that by 10 degrees. You're going to see much better results. And you might not think that 10 degrees is going to have that much of an effect, but obviously the data proves that it actually does. Now we'll look at the second flux. Now keep in mind with this one, we know that the chemistry is not optimized for this, so we weren't expecting as good of results, and that actually came true. One of the things to keep in mind with this, again, with that scaling, so 0.4 is the lowest on this. Remember on the slide before, 0.0 was the lowest, and the top end was 0.8. So we've got results here that wouldn't even graph on the other sheet. So same thing, when we have more time, it gets better. Totally makes sense, right? What we see with the pressure with this combination of flux and chemistry is 5.5 is still the best. 7 actually is the worst, and then 8.3 kind of falls in the middle, right? So now we know, okay, let's make sure we're not at a middle pressure. Let's either increase it or decrease it, but we're not the middle. And then temperature, the variability between the different temperature points is significant. We can see that 50 degrees is actually the best, but then 70 is better than 80 on this one. Again, this is why we're doing these experiments, because more information like this allows us to know where to set it up in the process. So as we look here, we look at these comparison slides, we can see what happens with the different fluxes in the application, what it starts at 1 second and 60 seconds, 180 and 300 seconds. Again, for the script, the 1 second is exactly the same, even though on here it looks different. But then as we go through, we can tell that the one where the chemistry and the flux are optimized together shows much better results much earlier than the one where it's not. So what are the results of this, right? When we look at traditional chip-on-wafer cleaning, a lot of that can take up to 90 minutes. This kind of shows, hey, let's spend some time doing optimization on the process, and we can reduce that up to 94%. Now, obviously, every application is different, but there's enough significant difference there that it's worth investing the time to optimize the process so we can get as much time back, if you will. Additionally, this shows that the spray pressure does not significantly increase the cleanliness, right? So maybe those lower spray pressures are really where you want to hang out, but of course we want to look at each application individually. Temperature showed a lot of variance, but we did see that increasing the temperature from 50 degrees to 80 degrees C showed a 25% increase in flux removal when the chemistry and flux are optimized together. And it's pretty obvious here to make sure that we have the right chemistry showed. For the test one, where we knew the chemistry and flux were working well together, showed much better results than the one where it's not. So that is obviously a very important starting point to make sure that those are in alignment with each other. CoWoS package cleaning, it requires an optimization of a number of different parts just in the chemistry side, right? We're going to look at that time, the temperature, the chemistry, the pressure, kind of aligning those with what's best for the application is going to provide not only quality results, yield results, but financial gain for your company. And it's crucial. Look, you guys are really smart. You guys are all smarter engineers than I am. But it's crucial to optimize the application to only change one variable at a time, right? If you change both time and temperature during the same experiment and you get better results, you don't actually know which one of those is actually changing the results of the testing. So one at a time, make sure that you determine your values on those results and then change the second. Kind of what this experiment proved is the importance ranking is chemistry is number one. We kind of thought that going in, but having a chemistry that's optimized for the application is definitely the most important. And then we get into the temperature, right? What is the variability on the temperature, the results of that, then the time, and then the pressure. So a couple questions that we get asked on this topic, what other variables affect this process? And yeah, we focused ours strictly on the chemistry, pressure, time, temperature, but there's a number of different variables that go into that. What is the nozzle type? What is the placement on those? What's the material compatibility? We've got a number of different metals in there. How does that relate to the chemistry, the water, the pressure, so on and so forth? And then rinsing. What is your DI water quality? How long are you rinsing? How are the parts set within the application to make sure that we're optimizing that, as well as ventilation? And is there a universal recipe for cleaning? This is a question we get all the time. And if there was, I could probably play more golf, but my golf game indicates that we get asked this question a lot. There is no universal recipe for cleaning. We want to look at all these variables. We want to dial it in. We may be able to set a universal recipe for something, but the reality is if we do that, we're probably costing you time and chemistry because we're going to set it longer to make sure that we get the cleanliness that you're looking for. But by taking the time to optimize each of these variables individually, then we can really get it dialed in. And that way you're not spending too much time on chemistry. You're getting the results that you want. You're not spending more money on power for your pressure and so on and so forth. So I appreciate your time. If you have any questions, please don't hesitate to reach out to any member of the KYZEN team. We'd love to talk to you about this.
Thanks, Scott. Thank you guys for watching this Tech and Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@kyzen.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.